Hello, this is Lewis McIntyre again. Today I'm going to talk to you about the axis of symmetry of the Lorentz transform. What? You didn't know the Lorentz transform had one? Well, it does. Let's get into it. My previous videos have discussed the trigonometric graphical solution for the Lorentz transform that I call the velocity triangle. The Lorentz transform is the basis for special relativity, but it was derived in 1892, 10 years prior, from the familiar Galilean transform, which simply relates measurements between two reference frames in relative motion. Henrik Lorentz applied unknown weights alpha, beta, and gamma so that both reference frames will measure the same speed of light. Solving for these unknown weights yields, after some messy algebra, the Lorentz transform. The Lorentz transform is a simple enough equation, but to date, no one has come up with a good graphical solution for it or even a good explanation. It's generally explained that space is contracted and time is dilated by relative velocity through some undefined process. However, both reference frames view the other's space and time being contracted or dilated. I have derived the velocity triangle, which very clearly conceptualizes the Lorentz transform and shows that it is the observer's measurement of an event in relative motion that is affected by relativistic Doppler shift, and not the event's time and space. This simple paradigm shift makes the special theory suddenly much easier to understand. The velocity triangle OAB, shown on the right, is based on the fact that all matter moves with a proper velocity equal to the speed of light, defining the direction of that travel as time. Relative velocity disappears as an independent variable, becoming a projection of one body's proper velocity onto the temporal axis OB and spatial axis BC of another body moving in a different direction through the Lorentz transform. For BC equal to velocity times time in S1, this defines the difference of direction, the angle beta, between reference frames S0 and S1, the sine of which equals V over C. This allows the Lorentz transform and Doppler shift to be written trigonometrically as shown. The Lorentz transform simply equates the measurement of event A in S0 to a measurement C in S1. There's only one problem. The velocity triangle works only for proper events in one reference frame, events which have zero x components, which transform to trajectories x equal vt in the other. Why is this? The reason is that the velocity triangle requires one point with common time in both reference frames. O satisfies this because at t equals 0, the two reference frames are co-located. With an x offset, this is no longer true, as shown at O prime. So what's the solution? The answer lies in the axis of symmetry for the Lorentz transform, something that I have discovered. First, we want to identify points in S0 that transform to identical times in S1, like the 0, 0 at O does. We then take the Lorentz transform for CT1 and set the result equal to CT0, then solve for the corresponding X0. I did this algebraically just to demonstrate the power of the trigonometric solution because the result is an algebraic jumble that doesn't tell us much except that such points exist. It's less messy when expressed trigonometrically, and we recognize the trigonometric beta function as the trig identity of the tangent of 1/2 the velocity angle beta, basically the bisector of the velocity angle. Next, we do the Lorentz transform for x1 using the value we just determined for x0 and determine that x1 is equal to and opposite to x0. We can then see that if we locate identical times on both time axes, the resulting x values are equal to the time multiplied by the tangent of beta over 2 with opposite signs. Now let me show you how to use the axis of symmetry to solve the generalized Lorentz transform with arbitrary values of x. We now draw a timeline through the S0 measurement A, parallel to the T0 timeline, to intercept the axis of symmetry at O. Next, we add an offset x1 equal to minus x0. And extend the offset timeline in S1 to intercept the axis of symmetry, also at O. We now construct the triangle OAB by extending the S0 x-axis through A to intercept the offset timeline of S1 at B and rotating BA normal to the S1 timeline to locate C. Finally, we subtract the CT0 and X1 offsets from OB and BC to obtain the Lorentz transform of A in S1 at C. The axis of symmetry allows the construction of velocity triangle from any reference frame by setting an X offset in the target reference frame and establishing a timeline through that point to intercept with a timeline through the X value in the source reference frame. Those two timelines will intersect at the common point O, setting up the velocity triangle for arbitrary X. Now I'm going to show you a shortcut solution. What I showed you is certainly a solution, but it involves a lot of graphic overhead. Let's look at bisecting angle ABC, also equal to beta, instead of AOB. First, we locate CT1 equals CT0 on the S1 time axis. Then we erect a temporary X1 axis in S1 at CT1. We proceed from A parallel to CT0 to intercept the X1 axis. And an equal distance parallel to the S1 time axis to locate C, the Lorentz transform of A. This certainly is a simpler and faster method. This procedure easily solves for multiple simultaneous points in S0. Points with the same time coordinate in S0 are simultaneous in that reference frame, such as A1, A2, and A3. But their transforms are not simultaneous in S1, shown by C1, 2, and 3. The further right points move in S0 from the axis of symmetry, the later their transforms will be in S1. The point on the axis of symmetry will be observed at the same time in S0 and S1, as shown by A0 and C0, which are exactly the same point. Points to the left of the axis of symmetry will be observed earlier in S1 compared to S0, as shown by A4 and C4. The transform points lie on a slope in S1, which is equal to the sine of beta. One of the more confusing aspects of the Lorentz transform is the sign of the V over C term in the two equations. When do you use the positive value and when do you use the negative? With the graphic solution, it's self-explanatory. To date, our transformations have been from S0 with velocity angle positive in the clockwise direction, and the transformations have been in a counterclockwise direction from S0 to S1. Now we're just going to go in the opposite direction. We do this like we did before, but now the unknown CT0 equal to the known CT1 direct a temporary X0 axis at that point. We proceed parallel to the CT1 axis to intercept the temporary X0 axis. And an equal distance in the direction of the CT0 to locate A. Note that the resulting X0 is smaller than X1 because this solution required the use of the negative expression. But then you didn't even have to think about that, did you? So I hope you enjoyed this presentation. Perhaps learn some things you didn't know about the Lorentz transform and the velocity triangle. If you want to learn more, please read my book, Writing on a Light Beam. You can purchase it on Amazon or via my website shown. Don't forget to press the like button. It helps make this YouTube presentation more widely available. Thanks for watching.